Now we are going to discuss some numericals on divergence, gradient, curl and Laplacian. So we have already covered what is the divergence operator, what is the curl operator, what is the gradient operator and what is the Laplacian operator. So now we are going to discuss some numericals. The first numerical is on finding the gradient of a scalar function, and the scalar function which is given in this numerical is small r, which is equal to under root of x square plus y square plus z square. So this is the form of the scalar function which we are given, and we have to find its gradient. Now what is gradient? Gradient of a scalar function, what is the formula? So if the scalar field function is given by capital T, we have already seen the gradient of a scalar function. It is equal to del by del x of t I cap plus del by del y of t j cap plus del by del z of t k cap. But now over here in place of capital T we are given with small r. So we have to find gradient of small r. So for gradient of small r we must find, so gradient of small r will be del by del x of small r I cap plus del by del y of small r j cap plus del by del z of small r k cap. So we will find the partial derivative of r with respect to x, then with respect to y, then with respect to z. So partial derivative of r with respect to x. Now partial derivative, it is operated on small r, and small r is given by under root of x square plus y square plus z square. So what will be the derivative? So we are doing the partial derivative with respect to x. So only x will be the variable, y and z they will be treated constant. So this is how we do the partial derivative. So partial derivative with respect to x. So when we will do its derivative, so the procedure is same. We are doing the derivative, so that will be equal to 1 by 2 under root of x square plus y square plus z square. This is how we do the derivative. We take the power in front and we subtract the power. We decrease the power by 1. So this is how we do the derivative. So we will get 1 by 2 under root of x square plus y square plus z square times the derivative of the function which is inside the square root. Now inside we have x square plus y square plus z square. What will be the derivative of this function with respect to x? That will be simply 2x, because y square and z square will be constant. So into 2x. So this will be equal to x divided by under root of x square plus y square plus z square. So similarly del r by del y. So we have found del r by del x, we have already found. We have to find del r by del y. So in the same way, del r by del y, it will come out to be equal to, so del by del y of under root of x square plus y square plus z square. So now in this, y will be treated as a variable, x and z will be taken as constant. So we will get 1 by 2 under root of x square plus y square plus z square into 2y. So that will be equal to y divided by under root of x square plus y square plus z square. So similarly del r divided by del z, it will come out to be equal to z divided by under root of x square plus y square plus z square. So gradient of r, so we have to find gradient of r. So gradient of r, it will be equal to del r by del x, which is x divided by under root of x square plus y square plus z square I cap plus del r by del y, which is y divided by under root of x square plus y square plus z square j cap plus z divided by under root of x square plus y square plus z square k cap. So this will be the gradient. Now 1 by under root of x square plus y square plus z square, it is constant in all the terms, so that will be equal to, so you can either leave the result of gradient of r up to this step, or you can simplify it. So we are simplifying this step. 1 by under root of x square plus y square plus z square, it is taken outside, and in bracket we will be left with xi cap plus yj cap plus zk cap. Now you can see over here r is equal to under root of x square plus y square plus z square. So this is nothing but the magnitude of the position vector. The magnitude of a position vector. So let's say you have any point in space capital P and its coordinates are x, y and z. So the vector from the origin to that point, it will be the position vector of that particular point, and its magnitude will be given by under root of x square plus y square plus z square, and that vector will be represented by r vector. So that position vector. So if we have this coordinate system and this is the point P whose coordinates are x, y and z. So the vector from the origin to this point P, it will be small r vector and its magnitude will be under root of x square plus y square plus z square. Now r vector will be nothing but xi cap plus yj cap plus zk cap. So here we have xi cap plus yj cap plus zk cap. So this is nothing but r vector, which is the position vector of a point whose coordinates are x, y and z. Divide by under root of x square plus y square plus z square, that is nothing but small r. So vector divided by its magnitude is nothing but the position, is nothing but the unit vector. So gradient of r, it comes out to be unit vector of the position vector. Now next numerical, it is on the divergence. We are given with the vector field which is given by x square I cap plus 3x z square j cap minus 2x z k cap, and we have to find the divergence of this vector field. So divergence of a vector field v vector, it is given by del vx by del x plus del vy by del y plus del vz by del z. Now the gradient of a scalar function, it always comes out to be a vector quantity, and we have seen over here also the gradient of a scalar function, it came out to be r cap, which has magnitude which is equal to 1 and it has direction which is r cap. So gradient of a scalar function, it is a vector quantity, and divergence of a vector field, it is a scalar quantity, and its formula is given by this expression. Now vx is x square, vy is 3xz square, vz is minus 2xz. So we will put the value expression for vx, vy and vz. So divergence of this vector field, it will be equal to del by del x of vx, which is x square, plus del by del y of vy, which is 3xz square, plus del by del z of vz, which is minus 2xz. So we will simplify it. Now here we have partial derivative with respect to x, and we have to do the derivative of x square, so that will be 2x. Now in the second term we are doing derivative with respect to y, and we do not have any y variable, and x and z will be treated constant because we are doing the partial derivative. So the derivative of this term with respect to y will be equal to 0. Now in the last term we have minus 2xz, and we are doing derivative with respect to z. So x will be treated as constant, so that can be taken outside. So the derivative of z with respect to z will be equal to 1. So 2x plus 0 minus 2x, that will be equal to 0. So divergence of this vector field is equal to 0. So this is a divergence less field. So this vector field, it is an example of divergence. The next numerical is to find the curl of a vector field, and the vector field is given by minus yi cap plus xj cap. So curl of a vector field, to find curl of a vector, we use determinant. So first row it is I cap, j cap, k cap. Second row is del by del x, del by del y, del by del z. And last row is the components of the vector field. Now x component of the vector field is minus y, j component, that is the y component, is x, and there is no z component, so that will be 0. So we will solve this determinant, so we will get the curl of the vector field. So on solving we will get first I cap. So del by del y of 0. So del by del y of 0 minus del by del z of x. So we are solving the determinant. Then minus j cap del by del x of 0 minus del by del z of minus y. And at last plus k cap del by del x of x minus del by del y of minus y. So in the first case we have del by del y of 0, which will be 0, then del by del z of x. So x will be constant because we are doing derivative with respect to z. So this will also be equal to 0. This will also be equal to 0. Here this will also be equal to 0. So only there will be k cap. So k cap del x by del x will be equal to 1, and del by del y of minus y, that will be equal to minus 1, and minus 1 into minus, that will be plus 1. So this will be equal to 2 k cap. So curl of this vector field which we are given in the numerical, it comes out to be equal to 2 k cap. So it has magnitude and it has direction. So curl of a vector field, it is always a vector quantity. Next we have to find the Laplacian of a scalar field. Now we are given with the expression of the scalar field and we have to find the Laplacian. So in the last lecture of Green's theorem, we have found what is a Laplacian operator. Laplacian operator is nothing but divergence of gradient of a scalar. So divergence of a gradient, it comes out to be equal to, when you evaluate this term, it comes out to be del square by del x square of t plus del square by del y square of t plus del square by del z, del y square, del z square of t. So this comes out to be equal to, so del square by del x square plus del square by del y square plus del square by del z square. This operator is called as Laplacian operator and it is written as del square. So del square, it is nothing but divergence of gradient. So this is operated on a scalar function capital T. Now we are given with the capital T expression. So we have to find the Laplacian. So we have to find del square of T. So del square of T is equal to del square T by del x square plus del square T by del y square plus del square T by del z square. So we have to evaluate every term and then we will put in this formula. So first we have del square by del x square of x square plus 2xy plus 3z plus 4. So we have put the expression of capital T in the first term. Then we have del square by del y square of x square plus 2xy plus 3z plus 4. Then we have del square by del z square of x square plus 2xy plus 3z plus 4. Now this is the double partial derivative. So first of all you will do the first derivative and then you will do the second derivative. So this is the double partial derivative that we are going to do. So first of all, when you will do the first derivative, first order derivative of this expression with respect to x, that will come out to be, so that del square by del x square, it can be written as del by del x of del by del x. So del square t by del x square, it can be written as del t by del x, and then we have again to do the partial derivative with respect to x. So this is nothing but del square t by del x square, means first you have to do the derivative of t with respect to x, then whatever the result you will get, then you have to do the derivative with respect to x of that result. So first you will do the derivative, partial derivative with respect to x, then again you will do its partial derivative with respect to x. So partial derivative with respect to x, it will remain as it is. So what will be del t by del x? So in this case, what will be del t by del x? So means we are doing derivative with respect to x. So that will be 2x plus 2y and z will be constant and all other terms are constant. So this is del t by del x. So partial derivative of t with respect to x, then again we will do its partial derivative with respect to x, that will give us del square by del x square. Now next term we have del square by del y square, that can be written as del by del y of del t by del y. Now what will be del t by del y? So we have to do the derivative of t with respect to y. So x square will be constant, 3z will be constant, 4 will be constant. So we will get only 2x. So we have to do derivative of t with respect to y. So that will be nothing but 2x. And at last we have del square by del z square. So del by del z, it will be taken out. So we first of all we have to do del t by del z, and then we will do the derivative of del t by del z with respect to z. So that will give us del square t by del z square. So first of all we have to find del t by del z. So what will be del t by del z? X square will be constant, 2xy will be constant, so only you will get 3. So the derivative, it will operate on 3z, that will be equal to 3. So del t by del z will be equal to 3. So now again we are going to solve this expression. We are going to do derivative with respect to x, partial derivative with respect to x. So 2y will be constant in this case, so you will get only 2. Then we are doing the derivative with respect to y, partial derivative with respect to y, and we have 2x. So this will be constant, so we will get 0, and at last term also we will get 0. So Laplacian of a scalar quantity, it has come out to be equal to 2. So Laplacian of this scalar field which we are given in the numerical, it has come out to be equal to 2. The next numerical is to find which of these three vectors they can be expressed as gradient of a scalar. So in the article of the types of vector fields, we have done two types of vector fields. First was divergence-less field, that is those vector fields whose divergence at every point is equal to 0. So that vector fields are called as divergence-less fields, and those divergence-less fields, they can be written in terms of curl of a vector field, curl of another vector field. So that we have already covered in types of vector fields, that for any vector field whose divergence is 0 at every point, so that vector field, it can be written as curl of some other vector field. Similarly, we have done the curl-less fields, that is those vector fields whose curl is 0 at every point. Those vector fields can be written as gradient of a scalar. So we have already done this concept. So now we are asked to find which of these vector fields they can be expressed as gradient of a scalar. Now any vector field, it can be expressed as a gradient of a scalar function if its curl is 0 at every point. So we have to find which of these vector fields, that is v1 vector, v2 vector, v3 vector, and we are given with these expressions of these vectors. So we have to find which of these vectors they can be written as gradient of a scalar. So any vector, it can be written as a gradient of a scalar only if its curl is 0 at every point. So first of all, what will be the main task is to find the curl of these vectors. That is, we have to find curl of v1, then curl of v2 vector, and then curl of v3 vector. So first of all, we will find curl of v1 vector. So curl can be found using the determinant. First row is I cap, j cap, k cap. Second row is del by del x, del by del y, del by del z. And last one will be the components of the vector. First component is x square, then is 3xz square, then minus 2xz. Then we will find curl of v2 vector. So curl of v2 vector. So that can also be found using the determinant. So second row will be del by del x, del by del y, del by del z. Then we have to write their components. First will be xy, then 2yz, then 3zx. Then we will find curl of v3 vector. del by del x, del by del y, del by del z, y square, 2xy plus z square, then 2yz. So first of all we will find curl of v1 vector. So we will solve this determinant, that will be equal to I cap del by del y of derivative of minus 2xz with respect to y. So when you will do the derivative of minus 2xz with respect to y, so we are doing the partial derivative, x and z will be treated constant. So we are just solving this determinant. So I cap, then we will get del by del y of minus 2xz. So del by del y of minus 2xz minus of del by del z of 3xz square. Then we will have minus j cap of del by del x of minus 2xz minus del by del z of x square. And at last we will get k cap, then del by del x of 3xz square minus del by del y of x square. So the first term del by del y of minus 2xz, it will be equal to 0. Then we are doing the derivative with respect to x and we have 3xz square. So this will be equal to 6xz. So derivative of 3xz square with respect to z, the partial derivative. So x will be treated constant. So this will be equal to 6xz. So minus, it will remain as it is, minus 6xz. Then minus j cap, derivative, partial derivative with respect to x, you will get minus 2z, and with respect to z, that will be equal to 0. Then plus k cap, derivative, partial derivative with respect to x, that will be 3z square minus 0. So we will get minus 6xz I cap plus 2z j cap plus 3z square k cap. So the curl of this vector field, it is not equal to 0. So vector v1, it cannot be written as gradient of a scalar. Only those vector fields can be written as gradient of a scalar function if the curl of that vector field is 0. So first vector, it cannot be written as gradient of a scalar. Now we will find the curl of a vector v2. So that will be I cap del by del y of 3zx minus del by del z of 2yz minus j cap del by del x of 3zx minus del by del z of xy plus k cap del by del x of 2yz minus del by del y of xy. So on solving this, first you will get I cap 0, and then you will get over here minus 2y, then minus j cap, here you will get 3z, then you will get 0, then plus k cap, here you will get 0, and here you will get minus x. So on solving this curl of v2 vector, it will be minus 2y I cap minus 3z j cap minus x k cap. So that is also not equal to 0, means vector v2 can also not be written in terms of a gradient of a scalar. So let's find for the last vector field. So this will be equal to I cap del by del y of 2yz minus del by del z of 2xy plus z square minus j cap del by del x of 2yz minus del by del z of y square, then plus k cap del by del x of 2xy plus z square minus del by del y of y square. So on solving this first term, we have del by del y of 2yz, so that will be equal to 2z, then minus, we are doing derivative with respect to z, so this 2xy will be constant, so this will be equal to minus 2z, then minus j cap we are doing derivative with respect to x, so here we have y and z, so that will be equal to 0. Similarly, second term will also be equal to 0 plus k cap. Here we are doing the partial derivative with respect to x, so this term, derivative of this term with respect to x will be equal to 2y. Then over here we have partial derivative of y square with respect to y, so that will be minus 2y. So this will be equal to 0 I cap plus 0 j cap plus 0 k cap, so that will be equal to 0. So curl of the third vector field, this vector field, it comes out to be equal to 0 at every point in the space. So therefore this v3 vector, this vector v3, it can only be written in terms of gradient of a scalar, whereas v1 and v2, they cannot be written as gradient of a scalar. In the similar way, you can also be asked to find which of the vectors can be expressed as curl of a vector field. So here you are asked to find which of the vectors can be expressed as gradient of a scalar, and to find the vectors which can be expressed as gradient of a scalar, we have to find the curl of these vectors, and if the curl is equal to 0, means that vector can be expressed as gradient of a scalar. But if you are asked to find which of the vectors can be expressed as curl of a vector field, so only those vectors can be expressed as curl of a vector field whose divergence is equal to 0. So instead of finding curl, in that case we will find the divergence of the vector fields, and we will see which of the vector fields, for which of the vector fields divergence is 0. So only those vectors whose divergence is 0 at every point in the space, those vectors, they can be written in terms of curl of a vector field.